Welcome to the webinar, Technologies of the Energy Transition, Direct Air Capture of CO2. I am Ángel Saz Carranza, Associate Professor of Strategy at ESADE Business School and Director of EsadeGeo, ESADE Center for Global Economy Geopolitics. This webinar today is part of a series organized collaboratively by EsadeGeo and the Repsol Foundation. We have two other webinars coming up soon. The first one on technologies of the energy transition, low and zero carbon hydrogen, which will take place on the 18th of June at 4 o'clock European time. And the next one will be on power to fuels. Fighting climate change will require a combination of well-designed policies, behavioral change, and innovative technologies. That is why we are launching this webinar series, to delve into some of the lesser known technologies related to the energy transition, focusing on those that may contribute to the decarbonization of some of the most challenging sectors. The first webinar of the series zooms in on technologies that extract carbon dioxide, the main greenhouse gas, either directly from the skies or from the industrial sites where CO2 is produced. With us are Dr. Julio Friedmann of Columbia University's Center on Global Energy Policy, a leading world expert on carbon management, who will dive deep into carbon capture, utilization and storage, and in particular, direct air capture. Jordi Pedrola is also with us, senior scientist at Repsol Technology Lab, who will be doing a brief introduction on CCS, carbon capture and storage technologies. We will start with Jordi Pedrola. I thank the audience following us here today, and please make use of the chat for any questions, which we will be taking at the end of both presentations. Jordi, the floor is yours.
Great. Thank you, Angel, for the introduction, and thank you to the ESADE and Repsol Foundation team for the organization of this webinar. In my presentation, I would like to give you an overview of carbon capture, utilization, and storage. So the first question is, what is CCUS? Carbon capture, utilization, and storage is a set of technologies that are aiming to avoid the release to the atmosphere of carbon dioxide that is generated in industrial processes or by burning fuels from power generation, and by storing it in suitable reservoirs or transforming it into various products. As the name indicates, the CCUS value chain involves, in a first stage, the processes that are needed for the separation of carbon dioxide from other processes, from other gases in streams throughout the industry. In the next stage, the carbon dioxide needs to be conditioned and compressed in order to be transported to its final destination. And finally, CO2 is stored permanently by injecting it deep underground, or it's used as a raw material for the production of certain products. Capturing carbon dioxide is not a new concept. The first commercial projects began in the mid-1970s, and nowadays there are over 20 large-scale facilities in operation with a capacity for capturing and storing close to 40 million tons per year of CO2. But why do we need CCUS? In the context of the climate crisis, the world needs to reduce sharply the global emissions of CO2 while securing a reliable energy supply, and taking into account that it's expected that the primary energy demand will grow at 25% in the next 2 decades. So this, of course, will not be met by a single technology, but a combination of solutions. For example, the increase of energy efficiency in all sectors, the spreading of renewable energy, the switch from coal to gas in power generation, and CCUS too, especially for hard-to-abate industrial sectors like steel, cement, and and chemicals and petrochemical sectors. In the sustainable development scenario from the International Energy Agency, which is consistent with meeting the goals of the Paris Agreement, CCUS provides up to 9% of the cumulative emissions of reduction between now and 2050, what translates into 2.8 gigatons per year of CO2 captured and permanently stored in this year, in 2050. This is 100 times the size of the present CO2 capture capacity, and this needs to be done in 30 years. CO2 can be captured from different sources. In the industry, CO2 can be separated from conventional, from concentrated streams, and we find examples of this in, for example, in the natural gas processing plants, in the production of bioethanol, and in some petrochemical processes, and also in processes where hydrogen is produced by the reforming of natural gas, like in the oil refining industry. It's important to note that the separation costs are inversely proportional to CO2 concentration. And in these streams, we have the lower capture costs. But as a counterpart, these concentrated streams are the least abundant in the industry. Diluted CO2 streams, on the other hand, have the highest share of total CO2 emissions throughout the industry, roughly more than 90% of the total. However, the cost of capture here is higher due to the more difficult separation. And we can find examples of these streams in the cement factories, in steel mills, and in general, in processes where fossil fuels are burned. And of course, CO2 can also be captured from the ambient air, which is called direct air capture. And as we will see later in this webinar with Dr. Friedmann, this option is technologically challenging because CO2 in air is in very low concentration, only hundreds of ppms, but it allows the removal of CO2 that is already in the atmosphere. Well, carbon capture is the stage that has the greatest contribution to the total cost of CCS, which in general lines can represent today approximately 70% of the total cost. And that's why there is a great technological development in this field at present. It's oriented logically into the scaling of these technologies that allow a substantial reduction in cost. Typically, there are three capture configuration options. First of all, we have the pre-combustion capture that involves the generation of a synthetic gas from the fuel and separating later the CO2 from it prior to the burning of the syngas. Post-combustion capture, where CO2 is separated mainly from nitrogen in the flue gas resulting from the combustion of the fuel. And another configuration is oxycombustion, where here the fuel is burned with pure oxygen instead of air, obtaining a flue gas stream that contains primarily CO2 and water, which is easier to separate than nitrogen. For each of these configurations, there are many technologies developed, and with different degrees of technological maturity, and they can be grouped in families depending on the separation principle. For example, we have the separation with the liquid absorbents, the use of solid sorbents, separation by means of selective permeable membranes, cryogenic separation, or even the use of molten carbonate fuel cells. At a commercial scale, capture is dominated at present by liquid solvents technologies that mainly use chemisorption using aqueous amine solutions. But in the post-combustion field, you can see here in the slide, there's the higher, as it this the post-combustion field has the highest decarbonization potential. There are many new and emerging technologies on development that are pretend to reduce the cost of separation below the 50 euros per ton barrier. Regarding the next stage in the CCUS value chain, the transport, it's important to mention that CO2 can be transported by pipelines or by ship. For pipeline transport, CO2 is typically compressed above its critical point, above 75 bar. And it's kind of a liquid with gas characteristics, which facilitates the transportation through the pipeline. This option is well established in countries like the USA, where there are some thousands of pipelines in operation. On the other hand, CO2 is transported by ship as a refrigerated liquid at pressures around 50 bars and temperatures of minus 25 degrees Celsius. Nowadays, there is experience in transporting food-grade CO2 in small vessels, but large vessels with capacities up to 7,000 cubic meters are on advanced design phase. And an important concept to keep in mind here is that unlike the first capture projects, which were linked to single facilities, the new projects are turning towards the hub concept, which will allow the establishment of a true market for the CO2. In Europe, for example, we find examples of this in the Northern Lights project in Norway, or in the Port of Rotterdam project in the Netherlands, or even in the Teesside hub in the UK. Well, and finally, CO2 is stored permanently by injecting it deep underground at depths are around 2,000 meters or more, or is used as a raw material for the production of certain products. Geological storage is already a reality today, and is possible, for example, in saline formations, in depleted oil and gas fields, and also for the enhanced recovery of crude oil, EOR, where in addition to using CO2 to extend the life of the deposits, an important part of the CO2 is retained in the geological structure. Regarding to the utilization routes, CO2 is used as a raw material for several options. In CO2 mineralization technologies, such as in the curing of concrete or in the production of synthetic aggregates, it can be also used in combination with a low carbon footprint hydrogen for the production of synthetic fuels or chemicals, what is called e-fuels or e-chemicals, or even it can be used in the production of polymeric materials. In all these routes, there are already projects and technologies on a commercial or pre-commercial scale. But however, the mineralization routes and the e-fuels routes are the ones that have the greatest potential for reducing emissions, because they are oriented to the production of products used in society in large volumes. Well, as a summary of this block, I conclude that CCUS is an option that allows us to go faster and in achieving the decarbonization objectives of the industry, and that is also an enabler for future products and businesses. It's not a new solution. There are already commercial projects for some decades, but for its large-scale deployment, there's some critical points. For example, we need the reduction of the cost of capture, the enabling of safe storage options, and developing viable utilization alternatives. And also, it's very important that the creation of a favorable regulatory environment in which public-private collaboration will be necessary to carry out these projects in the future. So thank you.
Thank you, Jordi, for this great introduction to this broad topic and helping us to go on towards to listen to our next speaker, the Dr. Julio Friedmann, as I was saying, probably one of the world's experts in CCUS and direct air capture. He is a non-resident scholar in one of the top centers, if not the top center on energy policy in the world, which is the Center on Global Energy Policy at Columbia University. And he is connecting from California. So Dr. Julio, the floor is yours. Dr. Friedmann, the floor is yours. Thank you very much for being with us.
It is my pleasure. Thank you so much for having me. Thank you to the Repsol Fundación, and thank you as well to EsadeGeo. It is an honor to be here, and I'm delighted to talk to you about this topic, direct air capture, which is, to my way of thinking, an essential pathway as we race towards carbon neutrality, as we work towards net zero. It is simply one of the things we know we will do and must do if we are to succeed. This is the backdrop against which this is happening. We have massive global protests asking for higher ambition for climate change at the same time as we face greater urgency, whether that is due to the fires in Australia or the floods in Florida or Houston. We know that there are already impacts from man-made climate change and that this will get worse. This has become a question of urgency. We need to move with highest possible speed in order to make progress, and ideally we would like to do so at lowest possible cost. In this context, carbon is the new grading curve, and net zero carbon specifically is the new baseline. Many companies have taken this perspective. Financial companies, tech companies, oil and gas companies, airlines, etc. And they have begun to build contracts and investment strategies around a net zero framework. And that includes the carbon footprint as a key parameter in making investment decisions. Many governments around the world have done similarly. Some nations have very deep NDCs, nationally determined contributions, in particular in the EU. Countries like the Netherlands and Denmark have between 40 and 70% CO2 reductions across all sectors with a goal of net zero. In the United States, the Clean Futures Act, which is in the House of Representatives, proposes a net zero power sector for the entire United States by 2045. 9 states in the US, including my home of California and my workplace of New York, have net zero power laws that require not just zero carbon power, but also net zero economies by 2045. And increasingly, we are seeing laws proposed that include CO2 removal from the air and ocean as a compliance mechanism for things like a carbon tax or a net zero standard. I point you specifically to the California low carbon fuel standard, which we will come back to shortly. Net zero has very simple math. If you emit anything, you must unemit an equal amount. What this means is that net zero commitments require CO2 removal. This is the simple arithmetic of CO2 removal. This diagram is from my friend Jennifer Wilcox, professor now at University of Pennsylvania. And it basically says if there are any residual emissions, they must be matched by negative emissions. If you want to accelerate the reduction of existing emissions, you can do through that by adding negative emissions. The math of this is daunting. If we want to reach a 1.5 degree target, we must remove roughly 10 billion tons of CO2 from the air and oceans every year, starting in about 2050. That's just the arithmetic. If we want to reach a 2 degree target, we still must remove 10 or 20 gigatons of CO2 by the end of the century. The 1.5 degree report from the IPCC says that we must remove between 100 billion tons and 1 trillion tons of CO2 to meet these climate objectives, depending on the scenario. It's worth knowing that that is also an enormous market opportunity. If you're being paid to do this at $50 to $100 a ton, 1 trillion tons is a lot of money. There are many approaches to doing carbon dioxide removal. Many of them you are already familiar with, things like trees, which do the job, things like biomass with carbon capture, which Jordi mentioned, more exotic mechanisms like the chemical weathering of rocks that are rich in magnesium and iron. Recently, direct air capture has emerged as a very important and promising technology. This is written about in great depth by the National Academies of Science and Engineering in the United States, and they published a deep report on all of these approaches 2 years ago in 2018. One of the things that they concluded, and is essential to understand for the framing of net zero, is that over the long term, we must put CO2 back into the geosphere where it came from. Carbon storage is geospheric return. If we put CO2 into the biosphere, that has real value, but I consider it to be more like carbon banking. It is short-term storage. Banking has real value, carbon banking has real value, but it is not the same thing as geospheric return. Over the last 2 centuries, we have pulled 2 trillion tons of CO2 out of the Earth's crust. Effectively, we need to put an equal volume back to stabilize carbon and climate. The ancillary benefits associated with biospheric storage are real. You get biodiversity and fresh water and all these other things. However, biosphere is limited by rates and the amount of volumes. It's also important to realize that natural pathways are not really natural pathways, they're really managed ecosystems. If we want to put large volumes of carbon in forests and in soils, then those actually require ongoing management, and they have real costs associated with them. It is also important to realize that climate change adds risk to that, because it makes the carbon stocks less durable over time and more prone to return to the atmosphere. So it is definitely the case that we will be putting large volumes of CO2 into the geosphere, and again, direct air capture is an important tool to do that. For the record, the National Academies reports concludes that of all of the total volume of CO2 removal required, 50 to 75% of that will be direct air capture, simply as a matter of volumes and costs. So what is direct air capture? It's a variation on what Jordi Pedrola discussed earlier. It is a way of separating CO2 from a dilute source. And essentially, air goes in, you add energy, and you use that to separate out CO2. On one side, you have low CO2 air. On the other side, you have CO2 that can be used for utilization or for geological storage. I will come back to that at the utilization piece at the very end, but we'll mostly discuss this in the context of geological storage of CO2. It's important to know that direct air capture has high costs. Those high costs are a function of the fact that we have very low concentrations of CO2 in the atmosphere. The partial pressure of CO2 is extremely low, about 400 parts per million, so the costs are high. This is not news to anybody involved in this work. However, it is still the case that we have to do it. And the good news is about 10 years ago, a number of companies launched to make direct air capture a commercial technology, and that commercially viable technology exists and is viable today. I will be talking about some of these companies later. Like Jordi Pedrola said, you can use a liquid solvent to separate CO2 chemically. Carbon Engineering is the company that has made the most progress with this technology. They project costs for their first million-ton plant to be on the order of $100 to $150 per ton. It is also possible to use a solid sorbent to adsorb CO2 and then to heat that and release it. Climeworks and Global Thermostat are two companies that do this today. In the case of Climeworks, the costs, depending on where they are, vary quite a bit. Their best offering today is about $500 a ton. However, they have an aggressive pathway for cost reduction and project that within 5 years, they will be less than $200 a ton. Global Thermostat is another solid absorbent technology. They have not yet built commercial facilities. However, they project their costs, again, to be about $100 or $150 a ton below when they reach their million-ton limit. For all of these companies, there are clear opportunities for cost reduction, and it is likely that we will see costs below $100 a ton within 10 to 15 years. Keep that number in mind. We will see costs below $100 a ton on the order of 10 to 15 years. There are other chemical pathways as well. Klaus Lochner, a long-term researcher and advocate, has proposed humidity swing adsorption and has a company called Kilimanjaro trying to commercialize that. It is also possible to simply compress CO2 out of the atmosphere. This has high energy costs, but in fact, you can just by changing the phase of CO2 make CO2 removals. When you do this work, the life cycle carbon footprint is an important consideration. You need a lot of energy to do this chemical separation or physical separation, and the carbon footprint of that energy is very, very important. All of these companies are proposing to do this with zero carbon energy, including zero carbon power and zero carbon heat. In most cases, they need 4 or 5 times the heat energy that they need compared to the electrical energy, and the heat must also be net zero carbon if they are to have a low carbon life cycle. This is just a quick comparison of the two dominant technology pathways: the solvent-based approach, in which you are looping a chemical solvent, in this case, sodium hydroxide, that separates the CO2 out. It absorbs CO2 and then separates it. And then you take that out to a calciner. You raise the temperature of the calcined carbonate, and that separates out the CO2. So you have these two loops as the process. For the sorbent approach, air goes in and is adsorbed onto a filter of some kind. You then add heat, and that releases the CO2, and out comes the CO2 stream. This is a picture of one of these devices. This is from Hinwil, Switzerland. This is the world's first commercial direct air capture plant. It does almost 1,000 tons of CO2 per year, but this separates out CO2 from the atmosphere. It does the work of about 36,000 trees with the footprint of about 1 tree. This technology can and will improve, and Climeworks, which owns this facility, is working to improve both the energy performance and the carbon performance. They have a facility that turns CO2 into stone in the subsurface. They are working with Reykjavik Energy at the Hellisheide power plant in Iceland through a project called CarbFix, and they are basically using the zero carbon electricity and the zero carbon heat from this facility to store CO2 underground. Here's the first unit. Here is the mineralized CO2. And if you want to, you can buy CO2 removal on their website. The largest proposed project is from Carbon Engineering. They announced a front-end engineering design study with Occidental Petroleum 2 years ago. And they announced that they would do a 500,000-ton project, and then announced 6 months later they would increase that to a 1 million ton project. This project is expected to break ground within a couple of years, and they hope to actually have operation as early as 2023 or 2024. This is what they believe this will look like on the site. Note this project has not yet been built. This is the third new species of these technologies. This is a pilot plant built in Alabama by Global Thermostat. This is taking CO2 from the air as well. This plant is designed for about 4,000 tons of CO2 removal each year, and again is a scalable module that can be repeated. Global Thermostat is expected to announce the first commercial plant shortly. It's important to know that the costs are high. It is also important to know that the costs can and will come down. Sustained research and development is necessary to bring these technologies to market more quickly and at lower cost. So we know the recipe to do this, and in fact, we have done it many times. Many people are familiar with the profound reductions in costs that have been accomplished in production of solar photovoltaic modules, just the PV facilities themselves. People may be less familiar with the cost reductions for the whole systems associated with this. And what you're looking at here is as a function of deployment, as number of gigawatts are deployed, you see already a dramatic reduction in the costs. This is basically about a 20% cost reduction for the integrated system. This is about a 12% reduction for each doubling. And the short answer is that with combination of research and development and through deployment, the costs will come down. There are good reasons to believe that this will happen as well with direct air capture devices. This analysis was done by the Rhodium Group. They published a report on this last year in which they used a modest doubling learning by doing growth rate, specifically 10%, as a projected option for thinking about the cost reductions for direct air capture. These are their findings. The original projected costs for direct air capture from 10 years ago were extremely high, and these were results published by the American Physics Society in 2011. Today, the anticipated costs for the first million-ton plants are much lower, and all of the people who I talked about before, all of the companies have ranges below $200 a ton for their first million tons of capacity. Rhodium takes a slightly more conservative assumption and believe the costs will come in between 325 and 125 million tons. It is important to say that these are the all-in costs. These includes the cost of capture, the cost of storage, the cost of compression, the cost of transportation. Using that 10% learning curve, they project doubling rates associated with this level of deployment. And this is the number that I want people to understand. Focus on 2030, 10 years from now. They believe that we will have costs ranging from $85 to $250 a ton, with a median value of maybe $150. This is extremely useful to know because it becomes a cap on the cost of managing climate change altogether. If you can really do climate change at this scale for $150 a ton, and if you scale it up to a gigaton, you can do it for even less, then you have a sense for what it costs. So let's look at the entire cost of decarbonizing everything. This is a recent marginal abatement cost curve that Goldman Sachs published at the very end of 2019. And this curve is basically looking at the total cost of everything, all of the cost of abatement for the entire global economy. And these estimates are based on the kind of integrated assessment models done by the IPCC. Beyond total CO2 emissions, we don't actually have other solutions. And in fact, the cost of doing that remains an open question. They put together a specific cost curve or a marginal abatement curve using a whole suite of CO2 removal technologies. Those included direct air capture, and they also included trees, and they also included mineralization. They also looked at carbon capture and storage as an option for things like the most expensive sectors, things like heavy industry, the costs that are out here on the order of $300 a ton. And this is what they came up with. This is an analysis that is done by the company Carbon Engineering, and I'm grateful for their slides and the use of their slides. And they said, what happens if you have opportunities at $150 a ton? That's the 2030 number, more or less, that the Rhodium Group projected for 10 million tons of CO2 per year. If you basically say, we're not going to do these costs, we think it's just cheaper to do direct air capture, then basically you can do all of this for a total of $3 trillion a year. The amount of money that you save from this wedge is on the order of $5 to $10 trillion saved in terms of avoided cost. In addition, if you use direct air capture to get this volume out here, and you cap the cost at $150 a ton, to get the entire volume would be $2 trillion a year. What this says is that for $5 trillion a year, you can basically get climate change solved. You would only use direct air capture for this expensive part of the wedge. You would only use direct air capture to remove CO2 out here. And things like trees and lower cost options are already used in this part of the analysis. So they are already deployed. Trees, soils, bioenergy with CCS already deployed. Direct air capture is used to manage the most expensive and most difficult parts of the system. That's good news. The bad news is we still don't have the policies that we need to make direct air capture markets. If we really want to see this happen, we need to align these markets in a useful way. The good news is this is changing very quickly. And there's three kinds of policies that you should consider. One of them is aligning with markets to make customers. The government can serve as the first customer and actually start buying direct air capture. And there are a number of governments considering this today in the United States, a number of governments in the European Union. There are other policies that can be used to get access to more customers, for example, creating standards of various kinds. There are also opportunities to create infrastructure, for example, CO2 storage project sites, industrial hubs and clusters, pipelines, these kinds of things. An important government policy is to consider investing in innovation. And there are now new US policies, UK policies, and Japanese policies that put money directly by name into direct air capture. Recently, the United States government has put $40 million into direct air capture by name with the Department of Energy and $85 million into direct air and ocean capture with the Department of Defense. It is also possible to create policies that allow direct air capture as a compliance mechanism. We've already talked about this in the context of net zero power. You can imagine the same thing for net zero industry. Nations like Sweden or Switzerland that already have very high carbon taxes could also consider adding direct air capture as a compliance mechanism there. And of course, countries can call out direct air capture as a component of their NDCs. This has not yet happened, but again, I expect this will change quickly. It is important to say, given the current global economy and the effects of COVID-19, we are not exactly sure how this will happen. It is good to see the planned EU stimulus package having appropriate ambition. We will see if other countries follow suit. One country essentially that is considering this for real is California. And they have set a net zero economy-wide goal, and in fact have done a study in partnership with Lawrence Livermore National Laboratory to understand what is needed. And basically, if they do complete decarbonization on everything else, they still have on the order of 125 to 150 million tons a year of residual emissions. So if they want to reach their net zero goal of 2045, they imagine that in addition to all of the other decarbonization they do, they will also need to do CO2 removal at a very large scale. This is what this looks like for them. They put together their own marginal abatement curve. It's important to know that only 25% of that can be gotten through natural solutions or managed ecosystems. The other, that is only 20%, the first 25 million tons. The other 80%, the other 100 million tons a year of removal must be done with carbon capture and storage. And of that, about 20% is done with direct air capture, either we're using geothermal energy or using other zero carbon energy sources. So again, bioenergy with CCS is an enormous part of the solution. Direct air capture is required to get things you cannot get any other way. It's also important to note that with this pathway, any failure of any kind on the prior slide, if any of this does not materialize, if they do not deploy as much removal or reduction as they want to in anything else, they simply need more direct air capture to fill the gap. They have clear-cut policies to do this today, which is good news. In particular, the low carbon fuel standard calls out direct air capture. And in fact, they have said that if you do direct air capture anywhere on Earth, they will consider it a California fuel. Today, the prices of this market are about $200 a ton. Even with the economic slowdown, those costs remain high and are expected to remain high. At $200 a ton, this is below, this is already more value than is expected from many of the costs associated with the direct air capture companies. And surprisingly, all of those companies and others are looking at creating projects that can take advantage of the low carbon fuel standard. It's also worth thinking about this in the context of other options, in specific, sustainable aviation fuels. We know that aviation is a hard to decarbonize part of the system. We have recently done an analysis on the levelized cost of carbon abatement and did a specific analysis on sustainable aviation fuels. This report we expect to publish in the next 2 months. But this is a preview of our finding. And specifically, we find that direct air capture today is already cheaper on a levelized cost of carbon abatement than all of the sustainable aviation fuels. If that's true, it may make sense to consider doing direct air capture instead of paying for sustainable aviation fuels. And in fact, the CORSIA process under the ICAO is already looking at these things. They're looking at an industry-wide opportunity set. They're looking to start with voluntary markets that are followed then by mandatory markets. And in this case, something like Article 6 creates a potential pathway to do this. Today, direct air capture is not a compliance mechanism, and that is unfortunate. If it were, then airlines would have more options and potentially at lower costs. Because it looks like, given our best estimates today, direct air capture is cheaper than the other options that are available. I want to end with just a short bit on hydrogen. And the reason I mention that is because hydrogen is becoming an important option. It may also be an opportunity for hard to decarbonize systems like shipping, and we are starting to see it become an option in other decarbonized, hard to decarbonize sections like steel. California is looking as that a large part of their negative emission strategies to make hydrogen from biomass. The EU stimulus package has a lot of going on hydrogen. Countries like Japan have made this a centerpiece of what they're doing, and we're looking about this for ships, trucks, and other things. Today, you can make hydrogen with CCS from fossil fuels. And in fact, today it is very much the lowest cost option to do this. If you look at steam methane reforming without CCS, adding conventional carbon capture like Jordi described makes it a little more expensive. Today, the green options are much more expensive, effectively 4 times the cost. And we published these results last year at Columbia. It is also the case, though, that you can do it with green electricity. And in some places of the world, in particular places like Sweden and Denmark, there's a low carbon footprint, and in some places the cost of hydrogen production are quite low and in fact compete with hydrogen cost for coal or for gas with CCS. In that context, you can think about direct air capture as a feedstock to a circular carbon economy. You can imagine in this context using low carbon hydrogen of any kind, whether it is from gas with CCS or from renewable energy electrolysis, using CO2 that is removed from the air and make a fuel out of it. And in fact, that is probably going to be a low-cost option. And indeed, the state of California is looking to do this. Many of the direct air capture companies, in particular, Climeworks and Carbon Engineering, have commercial partners to make synthetic jet fuel out of CO2 using zero carbon hydrogen. And power to X, or power to products, is something that will be discussed. Hydrogen is something that will be discussed in future EsadeGeo discussions. Ultimately, direct air capture is required. And we believe that low carbon hydrogen is also required. We are past the time where we have to consider moral standards. We have squandered the time that we had over the last 20 years to think about this. We really need more of all options. And in fact, things like efficiency, conservation, nuclear, CCUS, hydrogen, all of these things are needed. We really, however, need to focus on net zero. And in focusing on net zero, direct air capture is an essential technology. With that, I'm grateful for your time. I remain ambitious. I remain humble. And we simply need a lot more money. And we need to be open to ideas that come forward. With that, I look forward to your questions. And thank you for your time.
Thank you very much, Dr. Friedmann, for this fantastic voyage through direct air capture. We have quite a few questions coming in, so we're going to do perhaps a couple of rounds. Let me start with you, Professor Dr. Friedmann. Is there a risk? Is there a risk that direct air capture costs don't fall fast enough, and that industry decarbonization and CCUS costs fall faster, and therefore DAC, whenever it becomes more competitive, comes somehow too late to the or reduces the costs not quickly enough? And perhaps a more technical question: what are the main drivers of cost reduction in DAC, and in particular, differences between liquid and sorbent technologies?
Sure. So let me take the second question first, because it bears on the first question. There are many pathways to cost reduction. Because the energy costs are an enormous part of the cost for direct air capture, the fastest way to reduce cost is actually reduce energy costs. And as zero carbon heat and zero carbon electricity become cheaper, direct air capture will be cheaper. It is also important to reduce the energy penalty associated with doing this, so you can reduce the energy cost by making it more efficient. And that is where novel materials like better solvents or better sorbents can dramatically reduce the cost. All of the companies I mentioned and many other companies are working on that very hard. We know that there are better performing sorbents and better performing solvents. Getting those into the systems are things that need to be done. So yes, there are many pathways to reducing the cost. The important one, of course, is just scaling up. Mass production, larger scale projects also reduce the costs. In that context, of course, there is a risk that the cost reductions will not occur quickly. Let me say that that is a risk with all technologies. It is certainly a risk for the next generation of solar. It is certainly a risk for the next generation of nuclear. It is a risk for advanced efficiency pathways. It is a risk for biomass and biofuels. All technologies that can serve a climate goal face this challenge. And the recipe is always the same: invest in innovation and then align markets to get deployment quickly. That's always the recipe. It's the recipe for batteries. It's the recipe for solar panels. It's the recipe for windmills. It's the recipe for biodiesel. It's also the recipe for carbon capture and storage. It's also the recipe for hydrogen. It's also the recipe for direct air capture. Invest in innovation, create market alignment through policy.
Thank you. Thank you. And Jordi, a couple of questions for you too. One question was relative to Spain. Is there capacity to store carbon CO2 in Spain? And second question is, what is Repsol doing right now with respect to CCS?
Mm-hmm. Okay, regarding to the first question, in comparison to other parts of Europe, like in the North Sea area, where there's a long experience in hydrocarbon extracting from the soil, and also from injecting CO2 to underground. In the southern part of Europe, in the Mediterranean countries, there is less experience in that field, but there are some European projects in the Horizon 2020 program that are aiming to increase the knowledge of what are the possibilities to store CO2 in these areas. Well, and regarding to the second question, what is Repsol doing in CCUS? Well, we are aware that part of the solution in the fight against climate change must come from new developments, and CCUS is one of them. Although carbon capture and storage is a proven technology, with several decades of operating experience in some countries, there's a need to reduce the associated cost, as we have commented in the presentation. And in this way, Repsol participates in the development of these technologies as a member of the Oil and Gas Climate Initiative, the OGCI, with the investments made by the OGCI Climate Investments Fund. With this fund up to date, there have been several. They have several investment in startups. For example, the Svante company that has developed a new technology for CO2 capture from industrial streams. The carbon climate investments has also invested in Solidia. It's a developer of a special cement that allows the curing of concrete with CO2. Also in another carbon utilization company, the Iconic, has a technology for the incorporation of CO2 into polymeric materials. And the OGCI has also invested in the development of commercial projects for the capture and CO2 storage in the Net Zero T site in UK, and also in United States. There are a couple of more projects like the Levelised project and the Al Hills projects also related with carbon storage. Well, and internally at Repsol, we are working on identifying opportunities for the application of different CCUS technologies in our operations, analyzing in a first phase the development of pilot projects in the different industrial complexes.
Thank you. Thank you, Jordi, for that. Dr. Friedmann, do you see any possibilities also of small project DAC? Small scale, not in economies of scale sense, but in applying it to a home chimney or applying it on a rooftop or something like that. And a second question is, are there countries that you can see might benefit more and are more suitable for direct air capture?
Excellent. Happy to discuss. With respect to doing small projects and small scale DAC, I know that many of the companies, in particular Climeworks and Global Thermostat, are looking at these kind of small physical projects. And when I mean small, like I know that some companies are developing an application for your home, so that instead of buying CO2 for your soda stream, you can get your own CO2. It is also the case that both Global Thermostat and Climeworks have what is essentially a modular technology. As an example, the Climeworks system is a large number of units, each unit of which is 50 tons per year. So if you run a brewery and you're making beer and you need 300 tons a year, then you can buy 6 units and they'll provide the CO2 for you. So I do see this here. The real question is do they have the manufacturing capacity to drop the costs? Right now, making 1 unit is expensive. Making 1,000 units is a lot cheaper. And so they need enough sales to be able to get the cost down. Again, that is true for all of the companies. With respect to countries, there are 2 things that you need to do direct air capture and storage. The first thing you need is geological storage. You need a place to do CO2 storage. If you don't have that, you don't have a good DAC project for that. You might be able to use the direct air capture for concrete or plastics or one of the other technologies that Jordi Pedrola mentioned. But if you want to do storage, you need a storage site. The good news is that there is a lot of this around the world. We see between 10 and 20 trillion tons of storage capacity worldwide in conventional units. The next thing you need is you need abundant, low-cost, low-carbon energy. And there are many parts of the world that have that. It is easy to imagine places like the Persian Gulf, where you have a lot of solar resource, and you have places to store CO2 doing that. You can imagine a country like Chad or Niger in the Sahara Desert doing something similar. But you can imagine the same thing, say, for hydropower in places like Iceland or offshore Norway. You can imagine stranded natural gas assets in places like the North Slope of Alaska. You can imagine geothermal resources in Ethiopia or Kenya. Any place where you have low carbon, low cost energy is a place where you could do a direct air capture project.
Thank you. Perhaps last 2 questions. We might run over a few minutes on our schedule. What is the, you mentioned in your presentation, Dr. Friedmann, such more traditional techniques or technologies like reforestation as an option of extracting carbon directly from the air. What is, do you know of any, or can you imagine, or could you describe a cost-benefit comparison between reforestation and DAC through our technologies? And the second, go ahead.
Well, let me do that quickly first, and I actually prepared a slide that talks to some of this already. The thing about this is you should not think of these as really in a cost-benefit context. We know we're going to need all of these things, and we need much more than we can do with any of that too. So, but I'm happy to talk about it. There are different trade-offs between the system. Today, things like forests, some of that can be done at very low cost. But eventually you need to start taking over land. You need to start managing the system. So the costs follow a supply curve, and those supply curve costs go up over time. Okay? And eventually you reach a limit on how much you can do with land. The opposite is the case for something like direct air capture. It's born very expensive, but the more of that you do, the costs come down. And over time, you reduce those costs and have greater access. So at some point, there are trade-offs around these things. But for me, the most important trade-off is speed. If you need large volumes of CO2 quickly, then direct air capture is your answer, because essentially it's a much more intensive process. It is much more intensive in the same way that a solar panel is much more intensive than a tree, or a solar panel is much more intensive than corn. It is just more efficient at taking CO2. And so I use that example from Switzerland. Their facility does the work of 36,000 trees with the footprint of 1 tree. Mm-hmm. So if you need to get a lot of CO2 very quickly, it takes trees a lot of land, but it also takes them time to grow. If you want a more formal analysis, I'm going to share my slide again. And if I could ask the moderator to bring this up. The Goldman Sachs report actually looked at all of these things in the context of the full abatement potential. And they included things like the low-cost forestry options early on as a way to handle things like the emissions from agriculture. And that there are different options that have higher and higher costs as you go on. Things like using conventional carbon capture on things like natural gas plants or coal plants are options early on, but eventually you get things like heavy industry, iron and steel, or cement. You can use CCS, and direct air capture is the most expensive, but it is also the most flexible, so you can use it across the widest number of applications. So I think of these things as flatly complementary. You always want all of them, and you always want as much as you can get. It is not a question of either or, it is a question of yes and.
Thank you. The last question, close to our work here at EsadeGeo, is whether, and relates to your comment on we are lacking the policies for the development and implementation of many of these technologies. Now, one of the reasons probably of not having these policies is carbon leakage among countries. How do you think these policies can be developed without a global system of agreements that we're all going somehow to adapt and bear some of these costs, or without what the EU is thinking of currently, which is very problematic internationally, a border adjustment tax?
Right. So there is a very long answer to that, which I wish I could give, but I can't. So let me say two things. First of all, leakage is a real issue. One of the nice things is that now we have tools like remote sensing data and AIs that make it easier to recognize leakage when it occurs and tackle it. Second of all, border tariffs are one way to manage leakage, but they are only one way. There are other ways as well. For example, a club of nations, essentially what the Montreal Protocol did, works. And I can imagine a club around things like steel, where the primary steel corporations and the primary steel producing nations agree to a joint emission standards and create a club. That is a completely different way to do it. I can imagine a government contract for differences that instead of a border tariff actually paid for a higher value project that had lower carbon, and in doing so would create industrial incentives for domestic industry and actually help facilitate things like a club of nations. But to close with this idea, part of the reason why I am so enthusiastic about direct air capture is it just jumps completely past all of this stuff. You always know where the CO2 is going, you always know where it's coming from, and there is a meter. You know how much you're getting and where it goes. There is just no ambiguity. It is extremely robust. And in that context, if there is leakage, if there are border tariffs, if there are all these other things, direct air capture becomes a compliance mechanism by which people can avoid being silly. So I remain optimistic. If we have to wait for a global compact of nations, we will fail. And we can definitely get going on all of these other things today. As my former boss, President Obama, used to say, political will is a renewable asset. And we can take advantage of the renewable resource of political will to make changes in policy today that do not require all nations to act.
Thank you very much. We're going to close here. So I'm going to thank Jordi for participating. Thank you very much for being here with us. Dr. Friedmann, thank you also very much for connecting with us early morning California hours. It's an honor to have you, to have heard and listened to you, and had you in this webinar of ours. I also thank listeners and audience that have followed us, and I invite you to reconnect with us on the 18th of June at 4 o'clock to look at low and zero carbon hydrogen. Thank you very much.